We've been talking about ideal gases. We need to mention real gases. So, characteristics of an ideal gas are that it has no attractions between gas particles, and that the particles themselves have a negligible volume. At standard temperature and pressure, real gases behave much like ideal gases, and we can see that by looking at this graph, where we're comparing the molar volume of an ideal gas, which is 22.41 if you carried out one more significant figure, to the molar volumes of these other real gases. And you see that the molar volumes are quite close. In fact, helium hits it right on the nose. They're very close. Chlorine differs the most. When we get to high pressure or low temperature, we start to see some larger differences between what we expect from ideal gas behavior and what we actually see with real gases. And that relates to those two ideas of the ideal gas, that the particle size doesn't matter at all and that they don't interact. So finite volume, when we get to low pressures, the molar volume of argon is nearly the same as an ideal gas. We've got plenty of space in here, but when we increase the pressure, the more we increase the pressure, the more the size of the actual particles begins to matter. We're pressing them closer and closer together, and the volume of the individual particles is becoming a more significant portion of the total volume. And so that causes the molar volume of the gas to be above what is predicted by the ideal gas law. So here we can see a graph of that. Real molecules do take up space. Ideal molecules don't. So as we get to high pressures, and these are very high pressures, notice 400 atmospheres. That's 400 times normal pressure. That's a lot of pressure. As we get to higher and higher pressures, here the red line is ideal gas behavior, and argon, the volume, the molar volume, is higher than what we predict. And that is because of the actual volume of those gas particles. When we squeeze them closer and closer together, they occupy a larger and larger percent of the volume of the gas, and they are not negligible anymore. Well, the ideal gas law has some modifications. Johannes van der Waals, he lived around the turn of the 20th century, he modified the ideal gas equation to fit the behavior of real gases at high pressure by just adding in a little correction term here to account for the molecular volume. The molecular volume makes the actual volume, the real volume, larger than what the gas law predicts. Under kind of normal circumstances, conditions, it doesn't matter. But when you get to extreme conditions, it matters, and especially engineers, chemical engineers who are designing things, those little differences become significant. So he adds this little factor in. So B here is called the van der Waals constant, and it's going to be different for every gas because each gas has a different molecule size. I think I skipped, no? Okay, it's coming later. So that was talking about the volume of the particles. The intermolecular attractions become significant under some situations as well. At high temperatures, the gas behaves very ideally. The pressure is what we expect. At low temperatures, though, the pressure is often less than what the ideal gas law predicts. And this is because at low temperatures, are the gas particles moving faster or slower on average? Slower. They're moving slower on average. And so when they collide with each other, they're not moving as fast. And there are interactions between the particles of a gas. But when they're going really fast and bouncing off of each other, it's not very important. The slower they move, the more important that becomes. And the book gives the analogy of thinking about a billiard ball that's covered with something sticky. So you got like an adhesive or something on this billiard ball. And when the balls roll at each other and hit at high speeds, that tackiness on one of the balls doesn't matter so much. When they roll slowly, they might even stick together and not bounce off at all because they're interacting with each other. So what we see is at low temperatures, the intermolecular attractions between gas molecules become important. We're going to talk a lot more about what those attractions are. But they're just forces of attraction between molecules. Here in this graph we see red with the ideal gas and xenon in the green line. And as we get to lower and lower temperatures, the pressure predicted by the gas law, ideal gas law, xenon is actually lower than what's predicted. And that's because the xenon atoms are actually interacting with each other. And so they're not bouncing around like they should be. So there's another modification that van der Waals did. And we have another van der Waals constant. This one's A, so there's A and B. And that's also different for every gas because they all have different attractions. And so this one subtracts from the pressure. So here we have the corrected ideal gas law. This is an equation that can be used for real gases. Doesn't that look like fun? We're not going to do any with that. There's a table with, so for whatever gas you're using, you have to look up constant A and constant B and plug it into that equation.
And what is
N
N?
is the number of moles. So if you're going to solve that baby for N, fun, right? Doesn't that look like fun? It's like go get your math teacher to do it kind of a thing. Yeah. So there it is. There is a corrected equation of the ideal gas law to use for real gases, high pressure, low temperature. So what do I want you to know about all that? Well, I want you to know, well, let's go over this first and I'll tell you. So if we graph PV over RT, what does PV over RT equal? N. So if we graph N versus pressure for 1 mole of gas, the ideal gas would give us a straight line, right? But real gases, the ideal gas law is not exactly correct. So when we graph that PV over RT, it's not always 1. And so we see this varying curves and lines and things. And when the curve dips below the ideal gas law, that means that the most important factor here is the intermolecular attractions between the particles. When the curve is above, it means that the molecular volume is more important in skewing it from ideal behavior. Okay, so what should you know about this? So you should know that real gases do not always behave like ideal gases. At high pressures, think of you're squeezing the molecules together, and now the size of the molecules matter. Have I talked to you about Idaho? No, not Idaho, Wyoming. No, okay. So we were driving through Wyoming once. Well, we've done it more than once, but anyway. So we were looking in the AAA guidebook because there's a lot of nothing in Wyoming, and we're like, oh, we got to do something, right? This was before smartphones and games and stuff, and we didn't even have a DVD player or anything. So we were bored out of our minds. Driving from California to Minnesota with children in the car. I still don't believe we survived. But so we're reading about Wyoming. The population of Wyoming is about 400,000 people in the entire state. The population of Fresno, without Clovis, is more than that. So you think about all the people who live in Fresno spread out over a fairly large state. It's not like Delaware or something. You know, it's a sizable state. The density of people in Wyoming is very low. And you see that when you drive through there at night. You can drive for miles and not even see a light from somebody's ranch. I mean, there's nothing. Just land. It's kind of pretty land, but it's just land. Okay? So that's kind of like gases, right? So you think about the people in Wyoming. Would it really matter if they were all 98-pound weaklings or if they all weighed like 400 pounds? Would it, in terms of how much space they have in their state, would it really matter? No, the size of the individual people there is negligible. Now, what if you take all those 400,000 people and you start putting them into a big football stadium or something? Now is the size of the people going to matter? Yeah, because a 400-pound person takes up more space than a 98-pound person, right? The size of the people becomes important. So gases, when you compress them, when you round up all the people in Wyoming and you bring them all together, now the size of the individual person matters, whereas before it did not matter at all. So at high pressures where the gas particles are close together, the size of the volume of the individual particles matters. And it makes the gas not behave exactly like the ideal gas law predicts. At low temperatures, you have particles moving slowly, and they do have some attraction. At high temperatures, when they're moving quickly, they bounce off each other so fast they don't have time to be attracted to each other, right? Think about two people, and maybe they're destined to fall in love. But if one is traveling north on the freeway and one's traveling south on the freeway, they pass each other, but they were going so fast they didn't even notice each other existed, right? But if you're passing slowly in the hallway, you might catch that person's eye. They might notice you and something might happen, right? There might be some attraction there. So high speed, the attraction doesn't matter. Low speed, the attraction does. So low temperature, low speed, the forces of attraction matter. Okay, I went on for that way too long. End of chapter.